25, we're using the central limit theorem. And this is covered in section 5.4. This problem says we had a normal distribution. So if we have random samples of any size at all, then we know the sampling distribution of sample means is going to be normally distributed for any sample size that we use. We know that the mean of the sampling distribution always matches the population mean, and the standard deviation of the sampling distribution, population standard deviation, divided by the square root of the sample size. So looking at our problem, we were told we have a normal distribution in our population. We're given the population mean, population standard deviation, and we're going to be looking at samples of size 15. So here's the information listed from our problem. And for our sampling distribution, the mean is going to be exactly the same as the population mean. In the standard deviation, it's the population standard deviation divided by the square root of our sample size. And so there's our values for the sampling distribution. And the graph of our sampling distribution will look like a normal distribution. The mean is going to be right in the middle. And then these numbers out here are marking 2 standard deviations above and below the mean. So add the standard deviation twice to the mean to get the upper number. Subtract the standard deviation twice to get the lower number. 26 is similar to 25. We're going to be using the central limit theorem, and we're going to start off by finding the mean and standard deviation for our sampling distribution. And we're told the mean of our population, we're told the standard deviation of our population, and the size of sample we're looking at here are samples of size 27. So over in Excel, here's our given information. For our sampling distribution, the mean is always exactly the same as the population mean. The standard deviation is going to be population standard deviation divided by the square root of our sample size. And so there are our values. The graph is going to look normal. The mean is going to be right in the middle. And then notice there's 3 tick marks marking off 3 standard deviations. So add your standard deviation value 3 times to the mean to get the upper number. Subtract it 3 times to get the lower number. 27 is using the central limit theorem like 25 and 26. We have a population here that is normally distributed. We're given its mean, its standard deviation, and we're told we're taking samples of size 19 in this example. Here's the information from the problem. For our sampling distribution, the mean is going to be exactly the same as the population mean. The standard deviation, our population standard deviation divided by the square root of the sample size. And there are our values. Our graph of our sampling distribution is going to be normal. So the mean's right in the middle. And then notice there's 3 tick marks to these numbers out here. So add the standard deviation 3 times to the mean of the sampling distribution to get that upper number, and subtract the standard deviation 3 times from the mean to get the lower number. For number 28, we have a scenario here, and our end goal is going to be to find the probability that the mean from our sample is less than a certain amount. And so we have the information about the population. And in this example, we're looking at annual salaries for a specific job. So for the population, the mean annual salary is listed, and we have the standard deviation listed here as well for the population. And we're looking at samples of size 39. Now, by the central limit theorem, since we're looking at samples of size 30 or greater, it doesn't matter about the distribution of our original population. It doesn't matter if it's normal or skewed or uniform. It doesn't matter how the population is distributed at all. If our samples are above size 30, then the sampling distribution of sample means will approximate a normal distribution. And we know the mean of our sampling distribution will match the population mean, and the standard deviation of our sampling distribution population standard deviation divided by square root of the sample size. The key thing is we're working with a normal distribution here because we have a large enough sample size. So looking at our information in Excel, our population mean was this salary. This was the standard deviation. For our sampling distribution, it has the same exact mean as the population. And its standard deviation, population standard deviation divided by square root of our sample size. Now with this information, we know we have a normal distribution with these values here for the mean and standard deviation. So what is the probability then that in that normal distribution of samples, we would get a sample with a mean less than 60,000? The formula we're going to use, norm.dist, and we want to type in that value we're asking about, the probability of being 60,000 or less, then type in the mean of our sampling distribution, the standard deviation of our sampling distribution, and then true. And Excel will give back the probability of getting a sample with a mean, the value you enter, or even less. For number 29, we're going to rely on the central limit theorem. For the population, we're told what the mean is for the height of the population, and we're told what the standard deviation is for the population as well. And we're going to be taking a sample of size 75. Looking at the central limit theorem, since our sample is of size 30 or greater, it doesn't matter how the population is distributed. We know that the sampling distribution of sample means will approximate a normal distribution. And we know the sample mean will match the population mean, and we have this formula for the sampling distribution's standard deviation. So here's the information from our problem. And for our sampling distribution, we know the mean of that distribution will match the population mean, and the standard deviation will be the population standard deviation divided by the square root of our sample size. So now we can answer the question, what is the probability that the mean of a sample we gather, a sample of size 75, is going to be greater than 65 inches? So in Excel, we're going to use norm.dist, since we know our sampling distribution will follow a normal distribution. And we're looking for greater than 65 inches. We enter in the mean, comma, the standard deviation, and then true, and use those values for our sampling distribution that we calculated. And this is the probability that our sample will have a mean of 65 or less. Remember that Excel always returns the left-hand probability, the less than probability. So if this is the probability of having a mean of 65 inches or less, then 1 minus that is the probability of having a mean of 65 inches or more. And we're looking for the greater than, the more than 65, so that is our final solution. And number 30, we have a normal distribution. It's of the height of women in this example. We're told the mean of that population, and we're told the standard deviation for that population. And we want to compare whether it's more likely to randomly select one woman with a height less than a certain value, or to select a sample of a certain size, in this case 21 women, and the mean from that sample be less than that same value that we're looking at. So first, let's look at the one woman scenario. So just selecting one person from the population, our population is normally distributed. We'll use this formula in Excel, norm.dist. We're looking at the probability of selecting one person this height or shorter. And so then you enter the mean, and you enter the standard deviation, and we do true. And this is the probability then of randomly selecting one person from the population that is this height or less than, shorter than that. So now we want to compare that to the probability that we get a sample of 21 people, and the mean of that sample is less than that same value, 65.4 inches. All right, so first we need to find out about the sampling distribution. What is its mean and standard deviation? Its mean is going to match the population mean, and its standard deviation is the population standard deviation divided by the square root of the sample size. So now that we have the mean and the standard deviation for our sampling distribution, we know it follows a normal distribution by the central limit theorem because our population was normally distributed. So the sampling distribution is going to be normally distributed for any sample size. So our distribution for samples of size 21, the means of those samples will follow a normal distribution. So using our mean and our standard deviation here, we use that same formula. We're going to use that same value we're asking about, but use the mean and the standard deviation for our sampling distribution. And the probability then of getting a sample with a mean below that value is here, which is higher than it is for just selecting a single value from the population. And so this has a higher probability than just selecting a single woman, and that's how you answer the last part of the question here.